Okay, welcome back to the second week of our lecture. Today we will have 2 hours focusing on pollutants and emissions. We will discuss the kinetics, of course. We have a strong chemical background here. We'll talk about the different pollutants and so on. So what are the main pollutions, especially when we consider hydrocarbon fuels? So HC, also unburned hydrocarbons, carbon monoxide, nitric oxide or NOx, sulfur oxide, we have soot particulates, and finally, at least in our days, it's also considered as a pollutant. It's carbon dioxide, leading to the greenhouse effects. So we have a lot of different pollutants here with different effects on the environment and on the health. There are measures to get rid of these pollutions. And so we will discuss the formation of this pollutant, mainly NOx and soot formation. And we will discuss how to optimize the combustion process and which additional measures we can use to get rid of these pollutants. So when we look at the chemistry, of course, we have to consider the efficiency of the combustion with regard to unburned hydrocarbons. And we have the formation of polycyclic aromatic hydrocarbons, PAH, soot and particulate matter, and nitric oxide, nitrogen dioxide, and nitrous oxide, which we consider as NOx, and with a lesser extent, carbon monoxide. So when I landed here last week, Sunday at Delhi airport, there was heavy smog already. And so this is an article I have read, so it's from 30th November this year, so just 2 days old. So quite actual problem here in India. And here the focus of this article, that's not only a problem of Delhi region, but of course we have an entire sweep to all other northern states, including Bangladesh and so on. So this remembered me when I was young in the 80s, we faced similar problems with the acid rain, mainly from nitrous and sulfuric oxide or sulfuric acid produced by coal power plants in Czechoslovakia and former Eastern Germany. So it was behind the border, so we were not able from Western Germany to control this, and we have to live with the outcome of this pollution crisis. Nevertheless, there are measures to have clean combustion in combustion engine, and there are measures to have clean combustion with power plants. However, these measures always cost money, and that's more or less a topic which has to be governed by regulation. So it has to be mandatory to avoid pollutants, and then you could be able to get also rid of this problem here. So here in classical photochemical smog image over Los Angeles due to NOx formation. So we have nitrogen dioxide, which then is which absorbs solar energy, and then NO, nitric oxide, and atomic oxygen is produced. This atomic oxygen forms ozone, and this then reacts with hydrocarbons to produce hydrocarbon free radicals, and then these form then further species which have a lot of influence, especially with humans. And finally, NO reacts again with ozone to produce NO2. So especially the NOx formation here is very important if you want to get rid of this problem. But when you look at these two images here, industrial pollutions and soot from heavy-duty engines is of course also a very important problem. So soot, on the one hand, is used in industry for a lot of different processes, but here we more focus on soot as an air pollutant. So you see here heavy-duty engines, a train, a ship, airplanes, where a lot of soot is formed and is clearly visible at this black fume here. And the question now is how this is formed and how we can avoid this. So it was discussed already a little bit from Professor Zahu in the morning, especially when he has focused on his laminar diffusion flames. So when we look in premix flames, if we use proper conditions, there is no soot formation. Of course, especially in rich mixtures, this can happen. But again, if we use proper conditions, we can avoid soot formation in premix flames. In diffusion flames, it's quite complex. So depends on a lot of different conditions. It's difficult to control it in diffusion flames. Here often it's better to have measures to get rid of the soot after the combustion process. So soot is formed very fast within a few milliseconds. So, and again, we start with classical hydrocarbons. So propane, for example, C3H8H, sorry. Within milliseconds, we get very large soot molecules, which are quite heavy. So the smallest detectable solid particles have a mass of 2,000 atomic mass units. There's also then a transition from the gaseous to the solid phase. So it's a quite complex process, of course, and this we will see. And then I will try not to go too much into the chemical details, but at least I want to show you the complexity and the possible pathways we have. So either we can discuss the details afterwards, or at least you can take the slides to have some background information. If you ever face this problem in the future, you can start to look at this here before you have to find further literature. When we look at the energy part, so soot formation is entropy driven. We have a positive delta in enthalpy, but we also have a positive change of entropy. And then the condensed phase carbon forms as an aerosol. This is then kinetics driven. So there are possible different factors which supports here the soot formation, starting here from propane, single aromatic ring over this benzpyrenes, finally leading to large soot particles. So again, the scheme here, so we start with very small particles and have a lot of intermediate species here, and we have then finally the soot formation, and we can separate a molecular zone and this particle zone here when we look at the different processes. So this is a typical diffusion flame, which Professor Zahu has explained in the previous lecture. So we have a fuel flow and coaxial airflow. Then we have a reaction zone where we have optimum conditions. So here it's called premix blue flame. You can see it here. But then here in the molecular zone, soot particles are formed, and then we reach finally the particle zone where we have growing soot particles, but these are then oxidized again where we have excess air at the tip here. So this classical yellow light normally comes from soot particles burned in the upper part of the flame. So here we have more or less the formation, and then here we have the oxidation of fuel particles. So this was examined, for example, using taking some probes and looking at the size of the particles. So what we can see here, with proper flow condition, of course there is a formation of particles, so up to a diameter of 35 nanometers. And then in the oxidation zone, they are consumed. And here at a given height, only very small particles can be found. If we increase then the flow rate, so change just the flow condition of the flame, we see that this oxidation process is no longer effective. So even at much larger height of the above the burner, again, bigger particles can be detected. So as I said, for diffusion flames, it's quite complex to control the combustion process with the aim to avoid soot particles. And of course, it depends on the molecular structure, and one criteria is the so-called smoke point. So that's the flow rate with such a flame we have seen before. So you have to increase the flow rate until the combustion is no longer efficient, so the oxidation does not consume all the soot particles anymore. So you increase the flow rate, and at a given flow rate your flame starts to smoke, and the higher the flow rate, the more the lower, this way around, so the lower is the sooting property of the fuel. So propane simple hydrocarbons have a very high flow rate. So acetylene or toluene here, the aromatic substances, have very low flow rates. So here smoke, soot formation, and smoking starts quite early. So the main background here is based on some work starting in Germany in 1965, where they used mass spectrometry, a group of Hohmann and Wagner, and so they detected polyacetylenes up to C12H2, but of course species like C2H and C4H3. And based on this work, acetylene was chosen as a model substance from aliphatic fuels to produce soot. So, and acetylene and polyacetylene were the major components here. And they also find so PAH here with higher atomic mass units in this flame. So the classical setup was so we have either C1 species. We have seen it in the part of dealing with combustion chemistry, which can form in rich flames C2 species here. And of course, when we have larger aliphatic fuels, they decompose until they reach this C2 species. Here is acetylene. And then, based on this work, the formation of C4 species, finally C6 species was discussed, leading to aromatic a species which then may react with other species to form larger polyaromatic hydrocarbons. So the idea was that there is an attack of C2H on 1,3-butadiene, and this then finally forms the first ring, and with this ring structure here and further increase of 2 aromatic rings and so on was discussed. So the most important topic here is the first formation of an aromatic ring, so of benzene, and this can be either done by the way we have discussed before on the last slide, so the attack of acetylene on 1,3-butadiene radical, or this is what I have discussed on the last slide, vinyl radical with butadiene, with ongoing cyclization and so on. So we have a lot of different ways here to form benzene based on this acetylene chemistry. But it depends, of course, on the experimental condition, what we can see. So we can find an aliphatic structure here. We can find very complex molecules. Here we can find cyclic molecules, and finally we can get benzene itself. So there are possible pathways here, and the question is, of course, how these elementary reactions occur on the molecular level. You can see here, I just want to show you the complexity we have to discuss. It's a very, very, very complex problem, and of course, when you consider the reaction mechanisms, they have to include a lot of species, and they are quite complex. So, when we look at methane, ethane, and propane flames, it is clear methane flames produce most of the soot. Propane flames. And so when we look at propane, we can yield this propagyl radical, and with the others, methane, ethane, normally we end here at acetylene. So the question is then, which is more effective if we discuss soot formation? So this was the way we have discussed until now. And again, methane, ethane do not form so much soot compared to propane. So is this way eventually also of importance? So, and this was shown by Ravi Fernandez. You may know him in his PhD thesis. So this propagyl radical here, C3H3, is a very important molecule finally. So two of these molecules form one aromatic ring. So it's a very effective way to form radicals, and therefore this finally leads then to soot formation. Of course, as you see here, it's quite complex. So you have a lot of potential intermediates, a lot of different pathways. So how these two molecules, C3H3 plus C3H3, react together finally to give us benzene. And of course, we have a very complex reaction here. So, but there are possibilities to examine this in reactors. So here we use C3H3 iodide, which is then photolyzed by a proper laser. So we form instantaneously a huge amount of C3H3. So here we measure the absorbance of these species. So after the photolysation, we form a lot of C3H3, and then this reacts, and with a given reaction rate, the number of radicals reduces. So with simple assumptions, we get a second order rate, so that in terms of absorbance, we can calculate the reaction rate parameters. So quite simple second order fit. So we then get information about the reaction rate of C3H3 plus C3H3. Of course, there is not only the formation of benzene, we also have the formation of this phenyl radical plus H. But this can absorb, for example, absorbance of hydrogen atoms. And here we can then get information also about these reactions. So this work then from Ravi was start of a lot of other work from other authors. So they have examined in different conditions, different pressure, mainly with shock tubes, the reaction rate of these different specific species at higher temperatures, and I think with RCMs and so on at lower temperatures. So how can we resolve now this complex reaction scheme we have seen here? So C3 H3 plus C3H3 gives benzene, or C6H5 phenyl radical plus H. So, and one possibility is, of course, to use a time of flight mass spectrometer, where you suck out some of the molecules from the reaction zone and look what molecules you have. And this then can be continued that we have here to consider different routes here. So they call it even route. So where molecules with even number of carbon atoms reacts. So this is the way from Wagner. So acetylene plus C2H forms an C4 radical. This then reacts again with acetylene and we get this phenyl radical. Or following this C4 radical plus acetylene gives us benzene. And then there's the odd route, CH plus acetylene gives propyl radical, and this then can react with other species finally together here or with itself, C3H3 plus C3H3, either phenyl plus H or benzene. So we have seen from 1965 until today a lot of work was necessary to extend here the mechanism. So now we are at the stage of benzene, but this is of course still not Soot. So how do we yield then Soot? So first of all, question is how these cyclopentadienyl radicals, mainly based on fulvene here, can form also hydrocarbons. But again, you see this is quite complex. I do not want to go here into the details today. So a lot of different reaction routes are possible. And of course, this is quite a complex scheme behind this. But this is then part of the way to form higher hydrocarbons, here naphthalene. Again, based on this the complex reaction coordinate diagram. So first of all, two cyclopentadienyl may form these naphthalene, and these species here can form higher hydrocarbons. So we get an increase in the number of aromatic rings. And here I do not want to discuss too much, but of course we can look at phenyl radicals leading finally to naphthalene, and we can look at benzyl radicals leading finally to naphthalene. So we cannot discuss all the details here. So I'm lost here, and I think you may be lost here too. This is just to show you how complex this is. So, but nevertheless, so we have started with, for example, propane, and we are able to use proper mechanism at this stage to calculate the formation of naphthalene as a quite larger aromatic structure. And then this molecule reacts with other species. Finally, then we get this benzpyrene here. So we have already 4 aromatic rings, or here in this example we have 3 cyclic rings. So we are able to calculate, simulate in the molecular zone nearly all steps today using proper reaction mechanisms. So most of the processes are well understood today. So just here some details. So these phenyl radical here can react with acetylene, form this intermediate species here, and this then can form this naphthalene radical here. We have finally then on a minor root also naphthalene. So all the elementary reactions here are well understood today, and then starting here, this was the end product of the dominant root of the last reaction we have discussed. You can see how the formation of larger hydrocarbons can be described. So we have a lot of different reactions. So here's again another route how the possible growth of larger hydrocarbons can be described here. Benzene reacts with, phenyl radical reacts with benzene, forming this species. Then a radical is formed here, where again acetylene can attack, and then finally an additional ring is formed here, which then again can react with another acetylene molecule to build up again this benzpyrene. So we have a lot of different pathways included in the mechanism today. So we know today the formation of larger hydrocarbon structures, or aromatic rings structures, in the molecular zone. Then the question is, okay, how do these then continue to these soot particles? And one possible way is when we start here with this coronine, this can stick together based on this so-called zipper mechanism. So we call it also bucket catcher, and these half bucky structures named after the buckyballs, the fullerenes, have been detected also in flames. So we already have C30H10 structures, So a lot of hydrocarbons already in our molecule, and these larger structures then may stack together. So it's clearly visible that when we look here, for example, in this mass spectra, that we can see that there are specific higher amounts of mass molecules with a mass where these two structures here, this structure stuck together with a similar structure 3 times, 4 times. So it's just a stacking of large hydrocarbon structures. There's also the idea that there is a way of an ionic mechanism. So where primary ions attack our large hydrocarbon structure, form larger ions, because of the idea is, or the argument is, that the free radical reactions are much too slow. But first of all, the data is limited. There is not enough background information here. And when we look into shock tube experiments, there were no ionic species detected until now. So it's impossible theoretical way, but it cannot be based on experimental data. So until now we have discussed a lot of this growth here. So starting with acetylene and ethene, ethylene here, butadiene, hexatriene, and so on. So finally leading us to aromatic structures, benzene, naphthalene, benzpyrene, and so on. So all these have been found experimentally, and I hope I have explained to you now in detail the formation of soot on a molecular structure. So benzene is still discussed as a major precursor for particulate formation. The reaction models identify few properties critical to benzene formation pathways. We know that the fuel structure of the alkanes and alkenes is important for the soot formation. There are different routes we have discussed here. And finally, of course, especially when we talk about diffusion flames, a lot of factors are important with respect to soot formation. So these pathways are still under examination. So here we have first work presented in 1985 from Westmoreland and Franklach. Then there was an extension here in 1992, again for liquid fuels from coal and oil and coal. There was an additional class which was included here, and then we have now already work from 2007. So it's still not completed. So it's still under discussion, but you see that a lot of the possible pathways are included now. The main question is, so why do different fuels give different soot yields? So why is the smoke point, for example, so different? Gasoline 10 times more than heptane. An idea is that benzene is the tracer for soot. Propane produces more soot than ethane and methane, because here propane we have this propagyl route as an answer. And for rich premixed combustion processes, mostly small unsaturated hydrocarbons, especially in acetylene and ethylene, which are known to be precursors for the formation of benzene, and so they are also precursors to soot. So when we look now at newer combustibles, so renewable fuel, for example, so we have tripropylene glycol monomethyl ether, TBGME. We have this dibutyl maleate, DBM, which are molecules which may be used together with classical diesel fuel to optimize the combustion process, or want to replace finally diesel fuel. So we have synthetic biodiesel, we have methanol, ethanol. Yet you see that the percentage of fuel carbon converted to soot precursors depends strongly on the fraction of oxygen in the fuel by mass. So methanol, CH3OH, has a very high oxygen to carbon ratio, and when we look at this complex DBM, you can see there is quite a lower or much higher carbon to oxygen ratio. And this, of course, and this will be discussed after lunch, has an influence on the soot formation with these molecules. So with this, I would like to stop the first part of today's lecture here, but I'm open for questions if you want to discuss some topics already right now. So thank you.
So I just want to know more about observance time profile. So can you just explain observance time profile?
This one?
Means that initial rise and then it is falling sharply. So what does it actually indicate? So,
what does it indicate? So we have C3H3 iodide. And then we use a laser for photolyzation. So we form C3H3 radical.
Okay.
This is what we see here. The formation of this radical. And then the question is, okay, we have C3H3 plus C3H3. What is happening then? So, and two possible ways are the formation of phenyl radical plus H, or the formation of benzene itself. So both ways are possible. Other ways we have seen it's quite complex. So, and the decay here of this signal is related to the consumption of these radicals in this reaction.
So A is the reaction rate here, right? A, that y-axis part.
Yeah.
So y-axis part, it's decreasing means it's the consumption of.
Yeah. So that's the absorbance here. So here we have high absorbance. So we have formed these radicals, and then with specific second order rate law, these are consumed.
Okay, does it indicate it takes some time for this absorbance, mean that resolution part?
Yes, so of course the consumption of these radicals depends then on the specific elementary reaction rates we have to consider.
Okay, so actually what I'm asking this one, because while we are using the sensors, so we are getting some kind of plots for the temperatures also. So does this observance has anything related to the temperature? Means is it indirectly measuring the temperature, or it is actually measuring the observance?
Yeah, okay, what we finally have is the concentration. When we look at Lambert-Beer's law,
Okay.
of course the concentration depends then also on the temperature we have. But so we know this here, so this is so we have a known amount of these T3H3 iodide molecules, and so we know then of course the concentration at the beginning quite good.
Okay. Oh, my next question is, so we know the lot of negative things about the suit. What are the disadvantages of the suit? So how to focus on the advantages of suit? So because we cannot completely eliminate suit, so how to use that suit as for the benefit or in a positive way?
When you consider it with the combustion process,
Yes.
there is no positive way.
Okay.
So you should get rid of it. So
Okay.
and so in Europe, the regulations are so high at the moment that the air at the end of a combustion engine, at the exhaust gas of a combustion engine, is cleaner than the intake air.
Okay.
And considering the soot, for example, or particulate matters, here we have to use proper filters. And in these filters we collect these molecules and then they are reburnt finally. So there is no positive aspect with combustion. Of course, we use, as I've shown you at the beginning, soot in a lot of different industrial processes, but we should avoid to spread soot in the atmosphere if not necessary.
Okay. Thank you.
So, what I observed is like benzene is the major precursor for soot formation, benzene. So, is there any way that we can avoid formation of that reaction? The way like we are capturing it at the end by using catalytic converters.
Okay, here I have to say I'm not the expert, so it may be possible, but the applications I know mainly try to get rid then of the soot we have formed. As I've said, when you consider diffusion flame, especially in a diesel engine, it's very complex. In the molecular zone to stop the formation of benzene. So for premix flames, it's quite simple. You have to stay on the lean side or below a critical equivalence ratio. So if you are not too rich, then you do not follow this benzene formation pathway. But for diffusion flames, I'm not aware that it's quite simple to stop the formation of benzene at the molecular level already.
One more question, like if you have oxygen content, more oxygen content, like we have seen in the case of methanol and ethanol, can it be controlled benzene formation if I'm adding oxygen in by some way?
So this we'll discuss after the lunch break. Yeah, so maybe we can discuss this question after the next lecture. It's okay for you.
Okay, okay.
Yeah.
Thank you.
So no further questions? Okay, then enjoy your lunch. Thank you.